All right. It looks like it's about time to get going. I wanted to welcome you all to this community workshop on Microsoft's causal tools. My name is Emre Kujaman. I'm a senior principal researcher at Microsoft Research, where I work on causal learning. And I'm excited to be here with my colleagues to welcome the community and to learn from your experiences and see how we can improve our tooling and our research agendas to better solve real-world problems. So thanks again for joining. In this workshop, we're going to hear from people who are using causal inference in practice about their use cases and experiences. We're going to present a bit about Microsoft's open source efforts for causality and introduce a couple of new tools that I think you'll be excited about. And we'll close out the agenda by hosting some breakout discussions on industry use cases, where really we're hoping for some open discussion where folks who are interested in the same topics can come together and learn from each other. And we can also be there as well to learn how to improve our tools for your industries. We'll start off with our presentation about our open source tooling and just updating what we've done the past year and what's coming out now. And then we'll move on to fireside chats with a couple of domain experts, Jason Bagg and Stu Frost, followed by a deep dive into some really cool work on an autocausality library by Egor Kraev. And we'll then go into our breakout discussions. We'll be using the chat for asynchronous conversation today. So if you have any questions, please feel free to add your message in. We'll be monitoring that to answer. Thanks very much. And right now, I'll hand it off to Eleanor Dillon to get the first presentation started. Oh, one last thing. We will be recording the presentation. So just note that any video and audio will be recorded. Thanks.
Great. So I'm Eleanor Dillon. I'm an economist at Microsoft Research New England, and I'm part of the team that is working on the EconML package, which is one of several causal tools that we'll talk about today. So here at Microsoft and everywhere else as well, we've been seeing machine learning have enormous success in a number of areas by learning complex patterns from thousands or millions of data points. Is there a question or people are just tuning in? Okay. So there's many areas where machine learning has really empowered us to learn new things, to recognize objects, to translate, to have deep reinforcement learning in games like Go or StarCraft. But there's an area where machine learning alone has had less success, and that's these counterfactual predictions that we're all thinking about today. And the trick is really that when you're asking these causal questions, like if I give a depressed patient a drug, will they feel better? If I show an ad to a customer, will they buy this product where they otherwise wouldn't? Is that you only see one half of the story. So when you're asking AI to answer this question alone, they don't know what the comparison is. Either the patient took the drug or they didn't. And in order to know what changed when they took the drug, we need to figure out a way to figure out a reasonable approximation of this counterfactual other option. And asking the data to do this alone doesn't always work well. Sometimes you see similarities, things that look like a comparison when they really aren't. So that's why the tools that we have built think about getting humans and AI to work together. So causal analysis adds human knowledge to the constraints that we already have. It thinks about constraining the kinds of models and relationships that might be possible. Logical deductions can help us assess whether it's reasonable to think about a causal relationship or whether it's impossible that causality would flow that way. We can encode our domain expertise to begin to discipline and restrict what machines can learn. But within those restrictions, machine learning can add extra flexibility. So mapping data relationships that we might not have realized were possible, testing our hypotheses, and really expanding some of the traditional causal tools, which tend to be far more restrictive and think about linear relationships with predefined sets of features. So by bringing these two together, we can expand our frontier while keeping our reasoning and our human knowledge engaged. And Chung is going to tell us more about how these Microsoft tools that we've developed will do that.
Thank you very much, Eleanor. So I'm Cheng from Microsoft Research Cambridge. I'm a machine learning researcher here. So I'm going to talk about all our work in the integrated pipeline and how our work can provide different user experience so that we can be useful in all different scenarios. So one view to view the causal analysis pipeline is we have causal discovery, causal identification, causal estimation, and maybe you want to do validation as well. So across Microsoft, in all different locations, we actually work together, really enable the whole pipeline. So in particular, just to want to give you a sense of different projects, so that in our project, DECI is called End-to-end Causal Inference. Of course, naturally, we provide the causal discovery toolbox as well, which gives you the graph. And so for DoWhy, actually can do the causal identification and causal validation, and then we can take the causal estimation, which actually takes the identified graph part and do the estimation. And so we can do it together, or together we can provide a big pipeline. Okay, let's see how this type of pipeline can provide different user experience. So first, as an example, an economist who may know the confounders and what they want to estimate, for example, average return effect, these are the causal quantities we need to make decisions. So they have the input, know the whole historical data, and they can also, from domain expertise, find out the basic causal graph, like what are the confounders, etc. And so in this way, we can use the causal estimation. This can already solve all the problem. So our library, EconML part, EconML part of our library provides many of the state-of-art causal estimation methods. And with a different group of user, let's say a domain expert, meaning like a medical doctor or someone really expert in their own domain, not in machine learning or causality, they potentially know the full causal graph, like which nerve connects to which muscle, leads to which symptom, right? So they know the causal graph, they know the full data, but they don't have the causal concept, what are the confounder, etc. So in this way, you can use DoWhy, which combined with EconML together, can provide the whole pipeline to take such input and tells you, okay, what are the variables to condition on, and give you the causal quantities for your decision making. So this gives a more powerful tool to address the user who know their own domain, but not causality. Of course, the assumptions are not necessarily true, and you want to know, like, how can you trust the result? And DoWhy can also provide the function of causal validation. And in the end, of course, you can think about, actually, most of the user, they don't even know the graph, right? So a general data scientist or decision making who have a lot of data, this can be hundreds of variables, and they actually don't even know the causal graph at all. So no, like no graph knowledge completely, and also no knowledge about causality to how to arrange the graph into confounder and all these things. So this is the user experience like our project want to provide as well. We call it end-to-end causal inference because the user only comes with data, but we want to use our tool, use a whole pipeline, be able to tell users the causal graph. The graph itself can provide the insights to the user as well. And then from the graph, we can do the identification, estimation, validation as well. So we can provide all this output at once to be extremely insightful with minimum requirement of the user input. So in Microsoft, so you have different choices of such pipeline. So in Cambridge, we developed like you can use it as a single framework. We call the deep learning-based end-to-end causal inference. You can use it each of the modules separately as well to enable end-to-end causal inference. But among all the toolbox like DECI, EconML, and DoWhy, you can do like different combinations. So together we provide multiple end-to-end causal inference methods. And of course, not everyone want to make decisions like running code. Of course, like people, there are many people like data science that are very comfortable running these machine learning libraries, but to really like improve the user experience, let really the ultimate general audience be able to benefit from the causal tools we're building. There's a project called ShowWhy. It provides a no-code end-to-end analysis in a very user-friendly way. So next, you'll get more detailed updates about all different tools and how this tool may benefit you. And we look forward to your feedback as well.
Thank you, Cheng. I'm Amit Sharma from Microsoft Research India, and I have been working on DoWhy. I'll talk about a couple of updates that we have for both DoWhy and EconML. We thought that we'll share updates in this presentation since many of you would be aware of these libraries and hopefully may also have used them. So first of all, I'd like to thank all our contributors for these libraries because we've got some really good contributions from some of you in the audience as well, and that has helped these libraries grow to what they are right now. In the past year, we are very happy to continue focusing on the two main goals of DoWhy, identification and validation. So in identification, we have implemented the ID algorithm, which can identify causal effects for any DAG. And in validation, we are continuing to add more and more powerful methods. Again, validation cannot be sufficient. There's simply necessary tests or sanity checks that we can add. So we've added conditional independence tests, which can check the validity of an assumed graph. And we're also adding more sensitivity analyses based on some recent work, which has shown that you can use partial R squares, which are sort of very interpretable parameters to interpret the effect of an unobserved confounder on your analysis. And we also have an upcoming implementation of the same idea, but for non-parametric models as well, such as double machine learning, which is a nonlinear model. We are also looking at extensibility and making it easier to add external estimators, graphs from different libraries like DAGITI, and so on. And if you're interested, I'm also pointing to a case study that we did at Microsoft, where we used DoWhy in a problem of targeting messages to people who are most likely to benefit from that message intervention. Going forward and at a very high level, we are thinking about what are sort of other tasks that we can enable using the same fundamental building blocks that DoWhy has built. So specifically, we have built this pipeline of identification, estimation, and validation. And as we talk to users of DoWhy, we find that a very popular task is prediction. So often the goal is not just to calculate the effect of a variable, but to actually predict the outcome under different interventions. So we are planning to add this as well in a future update, and hopefully more tasks as we go along. Let me also share some exciting updates from EconML, which we just discussed earlier, which focuses on advanced estimation methods for causal inference. So one improvement has been that there's a new universal scorer called R-scorer, which can inform choice across different causal models in the library. The intuition is that many models essentially calculate a residual treatment and a residual outcome, which essentially controls for all the confounders. And then we are trying to estimate the relationship between these two. So the R-scorer tries to see which model is able to better capture this relationship between the residual outcome and the residual treatment. And beyond the open source library, we are also looking at new interfaces for EconML. So for example, there's a responsible AI dashboard in Azure that is focused on interpreting a fitted model and looking at what might have been the case if there was a causal change or a causal understanding of the same variables. So there you can look at the causal effects of different features, compare them, look at heterogeneous effects, and then also look at different cohorts and what policy or what features would work best for them. And finally, there's a ShowWhy that we will also share in more detail, which has wrapped up DoWhy and EconML in a nice guided interface. Uh, with that, I'll hand it over to Chow to talk about the DECI in detail.
Yep, thanks, Amit. So my name is Chow. I'm a researcher from Microsoft Research Cambridge. So I'm happy to talk about our new release from Microsoft Research, which is Deep End-to-end Causal Inference, or DECI, which is a new patented tool for scalable end-to-end causal inference, with a very comprehensive research report available on arXiv, and also a very easy to use open source code on GitHub. So to illustrate kind of say our new tool, basically, let's go back to the causal analysis diagram from Cheng. So basically, in causal analysis, we're interested in three questions: discovery, identification, and estimation, right? So the kind of say these three questions can be roughly grouped into two categories. The first one is causal discovery, which tries to uncover the causal relationships between different variables, right? And the second one is called causal inference, which contains both identifications and estimations, which tries to estimate causal effects of certain actions or variables on the outcomes. So this causal inference question is exactly the question that DoWhy and EconML tries to solve. So, however, in practice, if we want to apply causal inference to your problem, then one thing to notice is that causal inference requires or assumes access to the causal graph of your problem. And as mentioned by Cheng earlier, this is actually not always possible. So therefore, in practice, we need to find a way to combine causal discovery and causal inference. So, however, because these two methods have very different needs assumptions, therefore merging them together is actually a very non-trivial task. All right, so now, so in order to combine these two methods, there are two methods to consider. The first simplest thing you can do is simply by stacking, which means that you take the output of certain causal discovery algorithm as the input to causal inference, right? This is very simple to do. But the problem with this naive approach is that, so basically, you might find that this might cause problems of mismatch. For example, the assumptions of causal discovery algorithms and also the data format of causal discovery algorithms might be different from that of causal inference algorithms. So therefore, it might not be always the best thing to do to simply combine them by stacking. So therefore, we might want a new method that can perform joint modeling of all these three questions and try to complement DoWhy and EconML and perform causal discovery and causal inference in an end-to-end manner. Therefore, basically at Microsoft Research, we developed a new method called Deep End-to-end Causal Inference, or DECI, that allows us to jointly answer all these questions using only observational data. So the idea is that we take any observational data as input, and then we try to produce four causal quantities at the same time. So the first will be the causal graph, or the causal relationships between variables. And the second will be the functional relationships that measures the quantitative causal impact of one variable to another. And the third one will be the treatment effect of certain variables to the outcome. And finally, the recommended decisions for downstream decision-making tasks. So that would be the whole idea. And so there are actually 4 other, distinctive key features to our new method. And the first key feature is that when it comes to causal discovery, we can efficiently perform causal graph learning, which means that our method is scalable to hundreds of variables and millions of data points. So slightly under the hood of our tool, so this efficient graph learning is done by converting this very expensive discrete search problem into a continuous deep learning optimization problem, which can be solved, very easily and efficiently. So now the second key feature is that how to deal with graph ambiguity, because when you have only limited amount of data, it's often not possible to uniquely determine the underlying causal graphs, right? So therefore, so our method is able to deal with this kind of, say, graph ambiguity by learning a probability distribution over all the possible graphs that can explain the data. So that will allow us to take into account of uncertainty of graphs when we're estimating causal quantities. Our third feature is that we can perform efficient functional learning, which means that we can learn all these functional relationships between variables simultaneously when we're learning the causal graphs themselves. So in order to do that, we'd actually use deep learning machineries to model the impact of parent nodes in a graph to its child. So this allows us to scale to millions of points and also to model very complex and complicated relationships between variables. And finally, so when it comes to practical applications, you might notice that so when you gather observational data, some variables might be missing, and some variables might have mixed type data. So which means that some variables are continuous, and for example, and others might be categorical and binary. So our tool can also handle this kind of, say, missing data and mixed type data at the same time, which is very crucial to real-world applications when it comes to real-world scenarios. So at the end, our model finally is able to combine all these elements together to produce estimations of causal effects. So this was done by just let the treatment or certain actions to propagate through the learned causal graph, and then it will arrive and output an estimate of, for example, 8 or 8 of certain outcome variables. And of course, we will combine all the estimates from different graphs according to their probability in order to account for their uncertainty on these causal graphs. So, so you might think that this kind of tool is very complicated to understand and use, but actually in practice, they are very easy to apply to your problem because that's thanks to our open sourced API. So, so you can do all these kind of, say, data loading, model building, and model training all in one line of code. So after these kind of, say, model is trained, you can directly produce the underlying causal graph of your problem and also the treatment effects of your desired outcome variable, which will be very handy to your applications. So to summarize, so now we have a new tool which is called DECI, a deep learning based end-to-end inference method for causal inference. So which allows us to perform joint causal discovery and inference at the same time, which is scalable to large data and large graph, and also can handle missing data and mixed type data, which means that our method will be very practical and which will be high value for many practitioners in for your use scenarios. So you're welcome to try our method and demos in our GitHub link. So now I just hand over to Darren, who will talk about ShowWhy updates.
Thanks, Chad. Okay, so hi everyone, I'm Darren Edge. I'm a Director of Societal Resilience Research at Microsoft, and today I'd like to introduce ShowWhy, which is our end-to-end platform for causal decision-making by end users who do not need to be data scientists. And the idea is that we can empower domain experts to develop causal evidence through guided workflows that expose the core technical capabilities of all these causal libraries that you've just heard about in terms of DoWhy, EconML, and DECI, and build workflows that exploit different sources of randomness that we find in observational data, and allow us to develop higher standards of evidence that are necessary to inform evidence-based decision-making, evidence-based policy, and so on, especially in situations where it's not possible, practical, or ethical to run randomized controlled trials. One of the benefits of this approach is that we can build interfaces that help you to evaluate alternative approaches to their analysis, a form of sensitivity analysis, showing the impact of their assumptions. And this helps to overcome some of the pitfalls of observational data analysis that's analyzed retrospectively in terms of cherry picking, either accidentally or deliberately. And one of the main goals is that we can enable decision-making based on transparent and reproducible analysis, building interfaces that allow people to walk other stakeholders through the analysis process, through the decision-making process, as well as making all of the kind of computation behind the scenes, all the use of DoWhy, EconML, and DECI, and so on, available as a download in a Jupyter notebook. And that can be audited or used for reproduction by some causal expert as needed. So in terms of the ShowWhy demo, here's what the interface looks like. Currently, it's question driven, as you can see at the top. In this example, we're answering the question for the population represented by COVID patients. Does exposure to chronic disease cause the outcome of mortality to increase? And you can see that this is the question that the user has kind of posed at the start of their use of ShowWhy. I'll just play this video now. And so, ShowWhy is a guided workflow. You can see the workflow and the guidance on the left. The kind of second step in this workflow is just to give some initial definitions of those variables that are kind of hinted at in the causal question. So what is the variable that you're looking for in some future data set when you want to define your population, your exposure, and your outcome? And you're not limited to one. You can input multiple ones. In fact, the whole process is to encourage you as a user to consider multiple alternatives. Next, we're thinking about possible causally relevant factors that might affect the exposure and or the outcome. And then for each of those factors in turn that the user has kind of brainstormed as being potentially relevant, we asked to get a sense of whether or not it could cause the exposure and with what degree of belief. And then the same for the outcome, with what degree of belief. And this is a way of kind of beginning to elicit a causal graph of domain knowledge without necessarily starting with a canvas and asking somebody to sketch the kind of resulting DAG. Given those different degrees of belief, we can construct different kinds of causal models that incorporate kind of more or fewer confounding variables. And this again allows us to assess the sensitivity of our results to the choice of the causal model. At this point, it's now time to load in data sets that allow us to do the analysis against the question that we specified. So here we have data sets on various aspects of these kind of COVID patients. Here we're looking at a table of symptoms. And this is a kind of a general purpose data wrangling interface with different data transformation verbs that data scientists would use as part of their day-to-day work. But we're trying to expose them in a kind of a guided visual way such that users can progressively transform the data sets they have access to into the form that's required for causal inference. And so here we're just doing a simple step where we found an asymptomatic data column. We're doing a simple recoding to kind of flip those bits. And we're maybe kind of realizing that we can define our population differently, not just in terms of the population of people who had COVID, they were diagnosed with COVID, but maybe we can look at it in a slightly different way as those people who had symptomatic COVID. So next, we're going to do some more data processing. This is a table of chronic diseases, and it indicates which diseases were present for which patients. We just want a general idea of, was the subject exposed to any chronic disease? But again, you can imagine that you could define chronic disease differently in terms of different characterizations and so on, which again might demonstrate the sensitivity of your results to the precise definition of chronic disease. So finally, we're looking now at the patients table. This is the core table containing some kind of demographic information for each of the patients. We can now use the lookup operation to pull in other derived data columns from other tables to complete the set of variables we need to conclude our analysis. So I think we're going to jump ahead in this process now to the point where we've assigned all the data variables implied by the initial modeling. Now it's time to choose our estimators. These are presented in bundles at the moment, broadly along the lines of DoWhy and EconML. We can indicate whether we want confidence intervals and how many refutation tests we'd like to run for each of those estimates. And then, behind the scenes, using Azure functions, we're computing kind of these estimates in parallel and streaming the results to the client. And so on the top chart, what you can see is the estimated effect size is ranked in increasing order, along with indication of kind of where the mean and median lie. And then beneath that chart at the top, you can see the elements of these different kind of specifications for different approaches to doing the analysis that led to that particular estimate. We can toggle the confidence intervals on and off if we've computed them. We can make selections to understand kind of more about the kind of analysis that took place to produce a given estimate. And we can also load the results of a SHAP model that we compute behind the scenes to understand whether these different elements of our model specification led to systematic increases or decreases in the estimates we're observing. We see some quite kind of strong effects for different estimators here, some having a kind of positive kind of pressure on effect sizes, others having a negative. If we define multiple populations or exposures, here's a place where we can kind of toggle some of them off just to see like the sensitivity of the results. Once we're happy we've got a final set of valid estimates, we can move to the final page where we can run a significance test based on simulations and get some kind of understanding of whether or not the answer to our causal question is yes or no and why. And so we're trying to show why. Okay, so to conclude, we're trying to build this end-to-end platform for causal decision-making, and what you've just seen is an example of a causal decision-making process that's confirmatory in nature. It's led by a question. We're trying to show why, given some available evidence, some exposure causes some outcome. And this is an emulated randomized controlled trial method where we use DoWhy and EconML to control for the lack of controlled randomness that we find in observational data. But we don't just have kind of challenges deciding which interventions to make. We also have challenges of discovering candidate interventions that we might even want to consider. And this is where we need what we call causal exploration, showing why in a given data set, some variables might be seen to cause other variables. And we can achieve this using the DECI library that you've just heard about, and we're building this out as an independent workflow that we are going to be integrating into ShowWhy in the future. And similarly, after you've made an intervention or observed some event in the real world, we might need some causal evaluation, showing why that event may have caused some outcome over time. And here we're collaborating with researchers at Stanford University on the synthetic difference and differences method. So all of these methods will come together in a single package in the future. For now, we have a basic kind of prototype of our causal decision-making kind of step already available, open source at GitHub at github.com/Microsoft/ShowWhy, and we'd really appreciate your use and feedback as we refine and further develop this tool. So I think that's it for the introduction. Thank you for attending this part of the workshop. I hope you enjoy the rest, and more soon. Thanks.
Thanks so much, Darren, Chao, Amit, Cheng, and Eleanor for that presentation and update on our tools. And thank you to all of the workshop participants who are really being active in chat. It's super fun to see the discussion and see the energy around these methods and this topic.